Hello, welcome to this lesson on oxidation states. The question of the day, how do you know when a substance has been oxidized or reduced? All right, when we're looking at a full chemical reaction, you would have to know the oxidation states of all of the substances before and after to identify whether it had been oxidized or reduced. So if we look at, the classic ionic bonding reaction of sodium bonding to chlorine to make sodium chloride, we know at this point that sodium is going to lose electrons and chlorine is going to pick them up. They become ions, and then their electrostatic attraction is going to have them hang out together. The weird part is, though, that there are plenty of elements that have multiple oxidation states. It is not just the transition metals, it is also the nonmetals, which kind of stinks. Nonmetals can expand their octets, they can adjust how they share electrons, they can sometimes have a full transfer of there's a lot of rearranging that can happen in the nonmetals as well. So while in this case chlorine is a -1, chlorine can also be like a +7. So it's important for us to be able to identify exactly what the oxidation state of each substance or species is when we're talking redox reactions. There are a few rules to help us identify oxidation states, and it begins with rule number 1 that unbonded elements always have an oxidation state of 0. This is true whether we are talking about monatomic elements or diatomic elements. So if we have, like in the case of sodium and chlorine, here we have diatomic chlorine. The oxidation state of this chlorine over here is 0. That is because it is how it's found in nature. And then over here we have just plain old sodium atoms. Those are also going to be 0. Hydrogen is going to take on the +1 charge, which you should have picked up on because it's a member of group 1. There are some occasions where hydrogen will be -1, and that is when it is bonded to a metal. That's when it's a metal hydride. So if we had NaH, for instance, sodium is going to be the +1. It's a member of group 1. It's the only option for sodium. It's either 0 or +1. Hydrogen is usually +1, but it'll adjust based on the fact that it's bonded to a metal. So here it'll take on the -1 charge. Due to atomic radius and electronegativity, oxygen and fluorine will not really deviate from the standard, which for oxygen is -2 and for fluorine is -1. That should pretty much be expected. Anytime we have a neutral compound, the sum of all of the oxidation states is going to be 0. So think back to sodium chloride. In the case of sodium chloride, we have Na +1 and chlorine -1. +1 and -1 together will sum to 0. So that is kind of what we're getting at there. Number 6, the oxidation state of any ion, monatomic ion rather, is going to be equal to the charge of that ion. That kind of makes sense because oxidation state and charge technically are different, but we can kind of talk about them as if they're the same thing because of rule number 6 and 7. So if we have a lithium ion, a lithium +1, that is its charge and its oxidation state. And that is also true for polyatomic ions, except it's kind of a combination of rule 5 and 6, where the polyatomic ion has a sum of all of the atoms within the poly. They are going to sum to the charge of the poly. So in the case of NO3 -1, nitrate, the N and the 3 O's, all of those oxidation states will sum to -1 because that's the charge of the nitrate ion. If you have seen my video on molar mass, then you know that I use a QMT chart to figure out the molar mass of a compound. I will link that video in the description in case you're interested in seeing it, but the QMT chart, Q stands for quantity, M stands for mass, and T stands for total. And then we do that to figure out molar mass, or rather the sum of all the masses of all of the atoms in a particular compound. Here we're going to do that same thing, but it's a QCT chart. So instead of mass, we're subbing in charge. And this is going to help us to figure out the oxidation state of elements within a compound, because that's most often how you're going to have to decipher whether an element was oxidized or reduced in a chemical reaction. You'll have a full reaction and you have to kind of dissect it. So here we're looking for the charges of the elements within the compound SO2. So sulfur dioxide, we have 1 sulfur and 2 oxygens. Their charge is a little weird because I don't know the charge of a sulfur. Sulfur can change because it's a nonmetal and it's not one that has a specific rule that sulfur is always blank. So oxygen, we know from the rules, is always, always -2, and that's because of its electronegativity and atomic radius and kind of just its internal structure. We're going to multiply going across. So I know that all of my oxygens in total have to give me a -4, but I don't know what the sulfur total is. I do know from one of those rules, I don't remember the number, that our total for a neutral compound must be 0. So that's what we're working with here. So we're going to kind of like reverse engineer the table to get back to the charge of the sulfur. And we can just do like some simple, I call it baby algebra, because it's probably what you were doing in maybe even in like elementary school before you even knew that it was algebra. You have some mystery number, which would be this right here, minus this 4 is going to be equal to 0. It's -4 because it's a -4. Realistically, it would be plus -4, but I've already simplified it. So x minus 4 has to give us this 0 because we're working with a neutral compound. So x is going to be +4. The sum of all of my sulfurs is +4. I know there's only one sulfur, but I'm saying it this way because you'll see in a minute. So because I only have one sulfur, that single sulfur atom has a charge of +4. So the oxidation state of sulfur in SO2 is +4. Now we're going to do it again with something a little bit tougher. Here we have barium nitrate, and I've already filled in the quantities because I'm sure you're pretty good at this by now. Barium, we have one of those. We have 2 nitrogens and 6 oxygens. The barium is always going to be +2 because it's a member of group 2. Nitrogen's a weird one because it's a nonmetal without a rule, so I'm not really sure what it is. But oxygen will always be -2. I'm going to multiply going across, so my 1 barium is going to carry a +2 for us. All of the oxygens together are going to sum to -12, but I don't know what the nitrogen is. When we do the algebra, we have +2 from the barium plus the unknown number from the nitrogen minus the 12 from the oxygen has to give us 0. We combine like terms and we would have x minus 10 is equal to 0, meaning that x had to be +10. So I fill in a +10 for the sum of all the nitrogens. Let me say that again. I fill in a +10 for the sum of all the nitrogens. But in this case, I have 2 nitrogens. So I will have to take that +10 and divide it equally among the nitrogens, meaning that my individual nitrogen atoms are each carrying a charge of +5. So in the case of barium nitrate, nitrogen carries a charge of +5. I know that nitrogen usually likes to be -3, but in the case of barium nitrate, it's a +5. So between the 7 rules that I gave you plus the periodic table, you should be able to use this QCT chart to figure out the oxidation state and charges of really any element or atom within a compound. If you were looking for an ion, let's say, instead of your total coming out to 0, your total would be the charge of the ion. It's important to remember that polys have a charge. They are polyatomic ions. If you needed to know just nitrogen in nitrate, you could instead just set this total to -1 because that is the charge of a nitrate polyatomic ion. Also, if you have more than one atom of a particular element in your compound, like we had in the barium nitrate, it's important to remember to divide by the quantity of that particular element because the total charge is, like I said, the sum of all of those atoms. That is all on oxidation states. Please make sure to subscribe so you don't miss the next video. Leave any questions you have in the comment section below, and I'll see you in the next one. Bye.